Okay, hey everybody, and welcome to Heat Transfer. This problem that we have right here is a a heated plate that has a air moving across it. We know that the surface of it is kept at 140 degrees C. The temperature of the air and the velocity of it are listed over here. We have a drag force, and since we have a plate with a drag force moving through air, we know that we're probably going to have to use Reynolds number or Prandtl number, or any of those weird numbers and boundary layer conditions that you have to use. We're trying to find the electrical power needed to keep the plate at the temperature of 140 degrees. We also know that it's a one-sided heater. It's only exposed on this side to any airflow, which will come up at the end of the problem. And so any kind of electrical power that we put in is going to equal to the heat transferred out. So you don't have to do any weird electrical power calculations. You can just go ahead and do it in once. So, going ahead and doing this problem. If you wanted that diagram, go ahead and go back for a second and draw it out for yourself, because I'm probably not going to show it again for a while. So if we're looking for power transferred, you're going to use the traditional heat transfer equation, H times A all over Ts minus T infinity, which is something in an airstream, basically. So we need to find Q. But in order to find Q, we have to find H bar. We have this, we have this, we have this, but we got to find H bar somehow. And that's going to get a little hinky because this changes based on Reynolds number and fluid and where you are in the boundary layer and that kind of thing. So I'm going to go ahead and take air and find the properties of it. Properties. Rho is going to equal 1.2 kilograms per meter squared. That's actually about approximately. The Prandtl number is about 0.707, and the specific heat is about 1.007. Okay. Don't care about the units too darn much. It doesn't really matter for this problem. So the Prandtl number right here. This defines which equation you're able to use. There's multiple equations that use Prandtl number, but the one for this case is defined by which Prandtl number you have. And the ranges depend on if it's greater than 1, if it's much greater than Stanton number, and if it's between a range. But right here we have Prandtl number is less than 60, less than 0.6, which is one of the conditions. Which means that we can use the Chilton-Colburn analogy, which gives us an equation of CF over 2, which is equal to Stanton number times Prandtl number to the 2/3, which is also equal to JH, in case you happen to use that. Okay, so we're looking at this. We can use Stanton number, and we can reduce it into something that we can use a little bit, because right now we can't get Stanton number. We have Prandtl number, but we might want to mess with it a little bit too. Okay, so this is the equation you can use when your Prandtl number is in this range. If you're not in this range, then you have to use a different equation. So remember that. This is not universal. We know that Stanton number is equal to NUL, Nullset number, all over Reynolds number times PR. Well, that doesn't really help us very much. Oh, sorry. That doesn't really help us very much. But this one does. H all over rho V times C of T. Well, we have rho, we have the velocity, and we have the specific heat, and we're looking for H. So that looks like that'll probably be useful to us. So I'm going to go ahead and put this in here, and I'm going to move all this stuff over here. So CF, we're going average. We're not looking for a local thing because we're looking over the entire plate. Average. And the C is actually the friction factor, which can be calculated or given to you a couple different ways, but it'll become clearer here in a little bit. I'll get into that. Over 2 is equal to H bar all over rho mu infinity, velocity, which is u infinity of the air, times Cp times Prandtl to the 2/3. Oh. Alright, now we have our equation in terms of H bar, and we're looking for H bar. But the trouble is we still have the CF. So how can we solve for that? Well, there's an equation that hopefully the instructor gave to you, where CF over 2, that's a bad F, but that's an F, either way, is equal to tau S all over rho U of infinity squared. That's tau S of, okay, tau S. So, using this equation, you can actually find CF over 2. And this is the friction factor, if I didn't state that before. friction factor. What you can do here then is take this and solving it out, you can use a time constant, since this is a time constant basically. You can just use one time constant, and then rho we know is 1.2 kilograms per meter squared, and then we know u of infinity is 15 meters per second squared. Just like that. So, and if you solve this out, you have CF over 2 is equal to 0.0037. So now we have CF over 2, everything's solved for, and we just did this by getting around it. The only trick is to remember that you can use a time constant equal to 1. That's the only thing you got to do. Okay, so now, if we take this equation and rearrange it, you can get H bar is equal to CF over 2 rho u infinity CP times Prandtl number of negative 2/3. I mean, I could put this in a denominator, but negative 2/3 just makes it a little cleaner and straighter here. So, solving for H bar now, you have 0.0037, which we just solved for, 1.2 kilograms per meter squared, times 15 meters per second. Now, you may have noticed one thing. If I had just subbed this in for CF right here earlier, I could have canceled a few of these. But just to make it a little clearer and show how this equation solves out, in case something that goes funky or you're working in some other way. This is just a very clear step-by-step process, but you could just sub this in here and then cancel density and one of these velocities. And then 1.007 joules per kilogram Kelvin times 0.707, which is our Prandtl number, minus 2/3. If you solve that out, that is equal to 84.59 watts per meter squared Kelvin. Now you go ahead and put this back into our equation up here that we introduced, and you have the heat moving out of the bar is going to be equal to, the heat transfer rate is going to equal 84.59 watts per meter squared Kelvin times 0.25 meters squared, which was the width of the, oh, I probably didn't introduce that, show that in the diagram. The sheet of metal that we're working with has an area, A, equal to 0.25 meters squared. I apologize for that. I don't think that was in the diagram. Oh, maybe it was. But anyway, that's a repeat. That's the area there. And then that is multiplied by, oh, sorry, 140 degrees C minus 15 degrees C. Okay, and this will equal Q equal to 264.3.5 watts. And that's how much electrical power you have to provide in order to keep this plate at the same temperature. One little note here, you might see that this is with respect to Kelvin, the unit system here, but I'm using degrees Celsius over here. That's something that's neat about differences, because the difference in degrees Kelvin is exactly the same as the difference in degrees Celsius, simply because they're linearly related, because I could add on plus 273 here, 73 here, onto this one to make it Kelvin, but then I add on 273 over here too, but then they subtract away, so these become irrelevant between Kelvin or Celsius. So if you're an instructor or if you've never seen this before, you can go ahead and use Celsius when you have a difference, not when you're multiplying or dividing or something. If I was multiplying over here, then I would have to convert this to Celsius in order to cancel this. And there you go. That's how you figure out the heat transfer rate for a plate in a convected flow that has a Reynolds number associated with it.